You work 40 hours a week. You tap a glass screen and a package shows up at your door the next morning. You think it is simple. You think it is a straight line. You think your phone talks to a server. The server says yes, and a box starts moving. But that is a complete illusion. When your finger touches that screen, you are triggering a high-speed digital war zone that fires off millions of calculations across the planet in a single second. Most of us see an orange button. Very few see the planetary scale machinery working in the shadows. To understand what is actually happening, we have to stretch time. We need to take that single second and expand it into a slow-motion odyssey. Inside that blink of an eye lies the most complex engineering architecture ever built by human beings. This is the breakdown of the world's most expensive second. It starts with your finger. Your skin approaches the glass of your phone. The glass is backed by an electrostatic grid. Your finger disrupts the electrical field, changing the capacitance of the screen at a precise coordinate. The touchscreen controller chip detects this drop in voltage, translates it into coordinate data, and fires a hardware interrupt to your phone's processor. The operating system receives this signal, maps it to the layout of the app, and realizes you have tapped the button labeled Buy Now. Your phone's processor goes to work. It constructs a secure web request. This is not just a text message. It is a highly structured package of data called an HTTP POST request. It contains your account identifier, the unique item number, your location, and your security tokens. Before this data can leave your device, it must be encrypted. Your phone performs a series of complex mathematical operations using cryptographic keys, converting your personal details into an unreadable scramble of characters. This protects your data from being stolen as it travels through the air. Now, the encrypted packet needs a way out. Your phone converts the digital ones and zeros into high-frequency radio waves. These waves travel at the speed of light through the air, bouncing off walls and windows until they hit the nearest cellular tower or wireless router. The antenna on the tower picks up the weak radio signal, amplifies it, and converts it back into electrical pulses. From here, your request enters the physical backbone of the internet. It is no longer wireless. It travels through copper cables buried under asphalt, routing through local switching stations. The local station reads the destination address of your packet. It realizes the destination is a major data center miles away. To get there, your data must join the Great Digital Highway. It is routed into a fiber optic cable. This cable is made of ultra-pure glass, no thicker than a human hair. Inside this glass tube, a laser fires pulses of light. Each pulse represents a bit of data. The light bounces off the inner walls of the glass fiber, traveling hundreds of miles in milliseconds. If you're buying an item from a different country, these light pulses travel through undersea cables lying on the dark, high-pressure floor of the Atlantic or Pacific Ocean, protected by layers of steel and plastic. Before your packet can reach its destination, it must find the correct server. This is where the Domain Name System, or DNS, comes in. DNS is the phone book of the Internet. Your local network queries a series of massive server directories, asking for the exact IP address of the server handling your request. Once the destination is verified, the packet enters the front door of the data center. This data center is a concrete fortress. It is the size of several football fields, filled with endless rows of metal server racks, cooling systems, and backup generators. The air inside is kept cold and dry to prevent the machines from overheating. At the entrance of this digital fortress stands the load balancer. This is the air traffic controller of the Internet. It handles millions of requests every second. The load balancer does not process your order itself. Instead, it looks at the traffic levels of thousands of individual servers inside the data center. It instantly calculates which specific computer has the free capacity to handle your request right now and routes your packet there. Decades ago, Websites were built as a single giant program called a monolith. If one part of the monolith broke, the entire website crashed. Today, modern platforms use an architecture called microservices. Think of it as a hyper-efficient city filled with thousands of highly specialized workers. One worker only knows how to check prices. Another worker only knows how to count inventory. Another worker only knows how to talk to banks. These programs do not live on the same computer. They are scattered across different servers, and they communicate through standardized digital contracts called APIs. Your request is met at the gate by the API gateway. This gateway acts as the guide for the city of specialists. It reads your encrypted request, decrypts it, and identifies which microservices need to be called to complete your order. The gateway immediately sends out a swarm of digital messengers to start the process. The first messenger sprints to the fraud detection service. Before the system cares what you want to buy, it needs to verify that you are not a thief or an automated bot. This is not a simple check. Within milliseconds, a highly trained machine learning model analyzes your digital fingerprint. It looks at your IP address, your geographic location, the speed at which you click the button, the battery level of your phone, and your historical shopping patterns. It compares this data against billions of known fraud attempts. If the system detects even a tiny deviation from normal human behavior, the journey ends and your account is locked. While the fraud engine is running its analysis, a second messenger hits the inventory database. This is a massive database system that must track millions of items in real time. The inventory service cannot just say yes. It has to know if the physical product is actually sitting on a shelf in a warehouse near you. The system looks up the item ID and checks the inventory level. If there is only one item left, and another user in another state clicks buy at the exact same millisecond, the database must decide who gets it. This is the nightmare of database concurrency. To handle this, the system uses a distributed lock. For a fraction of a millisecond, it locks the inventory record, decrements the count by 1, and assigns that specific item to your account. If you pass the fraud check and the item is secured, the next messenger is dispatched to the payment gateway. This is the most delicate part of the entire process. Your credit card information is never actually stored directly on the retail servers in a raw format. Instead, it is highly protected using a process called tokenization. The system takes your card details and converts them into a one-time cryptographic token. This token is sent to your bank's computer network. Your token travels across dedicated secure networks, passing through financial clearinghouses. The bank server receives the token, decrypts it in a highly secure hardware module, and checks your account balance or credit limit. It asks a simple question: does this person have the money? If the bank system says yes, it reserves the funds and sends back a signed digital authorization token. This transaction happens in the time it takes to blink, crossing networks built by dozens of different financial corporations. All of these independent microservices must coordinate their actions perfectly. If the payment succeeds, but the inventory database fails to update, you would be charged for an item you cannot get. To prevent this chaotic scenario, the system uses an architectural pattern called a two-phase commit. Think of it as a digital marriage ceremony. A central coordinator program asks each service, "Are you ready to commit?" The database says yes. The payment gateway says yes. The shipping system says yes. Only when every single specialist says yes does the coordinator send the final command to write the changes permanently to disk. If even one service says no or fails to respond, the entire transaction is rolled back as if it never happened. To keep everything running smoothly without slowing down your screen, many of these tasks are decoupled using asynchronous message queues. Instead of making you wait for every single physical detail to be finalized, the system writes your order details to a high-speed message broker like Apache Kafka or Amazon SQS. These message brokers act as digital shock absorbers. They store your order in a highly durable log and immediately tell your browser that the order is confirmed. This allows the system to show you the checkmark screen while the slower physical processes run in the background. Up until this point, your purchase has been a ghost. It has been nothing but electrical pulses, light waves, and mathematical proofs. But now, the digital consensus crosses the most difficult border of all. It transitions from bits to atoms. The moment the message broker registers your confirmed order, it fires a signal to a physical fulfillment center located closest to your home. This is where the digital war zone triggers a physical earthquake. A fulfillment center is a massive warehouse, often spanning over 1 million square feet. Inside, there are no dusty shelves or human pickers wandering aimlessly. Instead, it is an automated hive of activity. When your order signal arrives, a warehouse control computer translates the digital request into a set of physical coordinates. Deep inside the facility, a drive unit, which is an automated robot about the size of a suitcase, wakes up. This robot drives along a precise grid marked on the concrete floor. It uses cameras and optical sensors to navigate, avoiding hundreds of other active robots moving in a synchronized dance. The robot locates the specific mobile shelving unit containing your item. It slides underneath the heavy shelf, lifts it off the ground using a hydraulic jack, and carries the entire shelf to a human picking station at the edge of the grid. A human worker stands at the station. A screen lights up, showing the worker exactly which item to grab from the shelf. A laser pointer projects a red dot onto the correct bin, so the worker does not make a mistake. The worker grabs the item, scans its barcode with a high-speed optical scanner, and places it into a yellow plastic bin. The empty shelving unit is then whisked away by the robot back into the maze. The yellow bin containing your item is placed onto a network of high-speed conveyor belts. These belts travel at speeds of up to 30 miles per hour, winding through the massive warehouse. Sensors along the belt read the weight and dimensions of the bin to ensure the correct product is inside. The bin arrives at a packing station. Here, a machine automatically constructs a cardboard box of the perfect size. A mechanical arm places your item inside the box, adds a layer of protective paper, and seals the box with heavy packing tape. The box then passes under a high-speed industrial printer. In a fraction of a second, the printer applies your shipping label. A blast of compressed air blows the label onto the moving box with perfect accuracy. The sealed box continues along the conveyor belt toward the sorting area. This is a massive, noisy system where the conveyor belt splits into dozens of different lanes. Overhead scanners read the barcode on your shipping label as the box flies past. Heavy mechanical arms or sliding paddles pivot in milliseconds, pushing your box down the exact lane dedicated to your zip code. The box slides down a metal chute where it is loaded into a large delivery truck. This truck does not drive straight to your house. It travels to a regional sortation center, where your box is sorted again alongside millions of other packages. The logistics network uses highly complex routing algorithms to calculate the most fuel-efficient path for every single delivery van. The system maps out every turn, every stop, and even avoids left-hand turns to save time and reduce accidents. The next morning, a local delivery driver loads your box into a van, follows a GPS-routed path, and walks up your driveway to place the package on your porch. We have reached a point in human history where the most complex engineering ever conceived is triggered by a simple touch of your thumb. We have abstracted this massive global system so perfectly that it has become completely invisible to the average person. When the machinery is hidden, we lose our sense of scale. We start to believe that instant delivery is the natural state of the universe. We forget that every purchase is a triumph of human collaboration, a global symphony of silicon, glass, copper, electricity, and kinetic energy. The magic is not in the orange button. The magic is in the architecture that makes the button possible. When you click, you are not just a customer sitting on a couch. You are the conductor of a global orchestra. You are the one who sets the city of specialists in motion. You trigger the invisible trial. You set the robots in motion. The world is no longer built of bricks and mortar alone. It is built of logic, light, and the incredible, fragile architecture of human intent. Next time you see that order confirmation screen, do not just look at the delivery date. Think about the digital messengers who just ran a global marathon for you in a fraction of a second. Think about the gatekeepers who protected your money and your identity. The 1-second war zone is always running, waiting for your next command. Stay curious, stay vigilant. This is the code that runs our modern lives. If you want to see the next layer of the invisible world, subscribe to Cypher Plane. Let us look deeper.